Okay, so this morning, I'm really going to set the stage for the semester. Okay, so I want to walk through the history of quantum mechanical thinking. This is chapter 1 in a book that I'm writing on how I teach this course. And so by the end of this lecture, you'll see why I decided to write the book I'm writing and why I teach the course the way I teach it. But I want you to back up to before Einstein, before Schrodinger, these names that you've heard of Planck and Boltzmann, even before Newton. It wasn't clear that math was a thing. In fact, this philosopher, Rene Descartes, wrote rules for the direction of the mind. He was thinking how to think. And this was pretty far back, 1626. And his rule number 4 was, we need a way to find out the truth. Okay. And that sounds pretty basic, doesn't it? But that's really relevant to today's world, right? How can you find something solid to stand on? You know, how would you know if something's true or false? Now, one of the concepts of truth, which I buy into, is called the correspondence principle of truth. And it is truth is that which corresponds to reality. Truth is that which corresponds to reality. And so the question is, how do you know about what's real? And how do you know if something corresponds to that? And mathematics is one way to do that. One way we realize that something's real is that it's repeatable. And math helps us to know if there's a pattern involved. And so Rene Descartes, in writing this and thinking about thinking, he says the human mind has in it something we may call divine, which means this non-human origin. I mean, it's just sort of this thing that's there in our minds, where these first germs of useful thinking come from. He can't really describe where the ideas come from. And maybe you have that too. You know, you're struggling with a problem and all of a sudden, out of the blue, you just know what to do next. Okay, that's what he's describing here, sort of this spark of inspiration, we call it. And his spark of inspiration was mathematics. He was like, wow, mathematics really corresponds to the world around us. So mathematics is one way of finding out the truth. It's not the only way, but it's one way of finding out the truth. And so then he wrote a book analyzing the motion of objects. And it's called geometry. I mean, like, he wrote geometry. And where do you think the word Cartesian comes from? It's Descartes. So the Cartesian system, X, Y, Z, comes from his geometry. And this is before Newton. In fact, this geometry book is what inspired Newton to begin mathematical study. And Newton came up with calculus. We talk about the apple falling on his head and him discovering gravity, right? But it was his mathematics and taking algebra and geometry from Descartes and turning it into calculus really let science take off. In fact, this germ of thinking, this mode of thinking, mathematics, jumped from Descartes to Newton. And so the rest is really history. Classical physics came from Newton. The motions of bodies banging into each other. In fact, it was so successful that we really thought we could predict the future if we knew the position and momentum of every particle in the universe, that everything was determined, just like billiard balls banging into each other. And it was so common. This is a poet in England, probably the second most quoted poet, English poet behind Shakespeare. It's Alexander Pope. And so this tells you how famous Newton was because of his successful physics and calculus. He wrote, nature and nature's laws lay hid in night. And God said, let Newton be, and all was light. Okay, it kind of playing off the Genesis account where God said, let there be light. He said, let Newton be, and then everything was illuminated. So that's how successful Newtonian physics was. We felt like we knew everything there was to know. And so this method of thinking went from Descartes to Newton. This germ of useful thought, mathematics, was caught by Newton, and then further developed by Boltzmann. Boltzmann started applying it to thermodynamics, physical chemistry. And then from Boltzmann, this idea of quantum mechanical thinking. What is a quantum? Quantum is just a packet, like like we don't have a half a penny in our currency system. Penny's the smallest piece. So a penny would be a quantum of US currency. Right? So that's the smallest unit. So a quantum is just that smallest unit. And Boltzmann used it as a mathematical trick. Instead of doing something using straight up calculus, he did a numerical technique where he assumed that gases could only have certain velocities, certain quantum of speed. And it was just a way to simplify the math so that he could do a sum instead of an integral. Okay. And he said, this isn't supposed to be anything real. I'm not saying that gases can only have certain speeds, but it simplifies the math and helps me see where this calculation is going. So he's the first one to really think about quantized energies. And then Max Planck used that idea and used Boltzmann's mathematics to solve a spectroscopic problem. And a lot of people will give credit to Planck, Max Planck, as being the father of quantum thinking. And in fact, he is. He's the first one that solved a quantum problem using quantum math. But it was Boltzmann's equation that he used. And Boltzmann's equation was based upon this idea that gases can only have certain velocities. This math idea also was developed by Werner Heisenberg, who solved a lot of the quantum mechanical problems using matrix multiplication, matrix mathematics, but he didn't have a care about what the math meant. He was just using math as a tool. So he didn't really think about the quantum part. He just focused on solving the mathematical problems. He was a fantastic mathematician. But Louis de Broglie, that's how you say that name, he was thinking about what could cause this quantum effect in nature. And he loved music. And so he was thinking about standing waves in a violin and how you can have the fundamental tone of a string, and then you can hold it halfway down and hit a resonance. And you could draw these standing waves on a violin string. And he said, what if the electron orbit around an atom was like a violin string and had standing waves? And so he created a new germ of thought of this standing wave idea that could explain the quantum energies. And Schrodinger was impressed with that and grabbed that idea and solved some more quantum mechanical problems. And so then this became a mechanical idea. When you say mechanics, you have a method for the science working. When you just say quantized energy levels, you're really at the level of quantum theory. You have a theory that this nature is quantized, but you don't really have a way or a mechanical system to think about. There's no model. But when they added waves in, now they had a model. And so if nature is behaving like waves, then we talk about quantum mechanics. It's the wave mechanics added to quantum theory, and that's where the word quantum mechanics comes from. So quantum theory is nature works in discrete energy levels, and wave mechanics is the interactions of waves, just like you would see on the top of a pond, and the waves interacting. And you combine the two, and the wave mathematics can explain the quantum theory. So this was the problem that Planck solved. This is black body radiation. And we see here this Planck distribution matches what is seen in nature. So for a hot object, you have this shape of the light that's emitted. It has a maximum here, and it tapers off as it goes to long wavelengths. Now this is a very hot object because it's in the visible region, actually in the UV, giving off a lot of its light in the UV. But notice out here in the long wavelength region, the match between these curves is pretty good. Well, we had data down here. Let's just draw some data points in there. And so we had some data points at long wavelengths. And Rayleigh and Jeans plotted a curve to fit those data points. They didn't really know why that model had, if that model had any physical significance, but they were just finding a model that fit the data. That's what we do. We have 4 data points. We figure out a line that goes through there, We want things in that model to match reality, like temperature, okay, wavelength, any kind of energy conversions like Boltzmann's constant and so on. And so the Rayleigh-Jeans law matched this data here, but if you'll notice in the denominator, it has lambda to the fourth power, so wavelength to the fourth power. So what's going to happen to this equation when the wavelength gets small? Right, so when this wavelength gets really small, this blows up to infinity. And that's this curve right here. You see it going up and up and up and up. So that's the Rayleigh-Jeans law. It matches the data down at long wavelengths, okay? But at short wavelengths, it goes to infinity. It's a function of temperature. Even at really low temperatures, it's still going to go to infinity. And if you work out the units, this right here ends up being an energy density term. It's how much energy is being emitted. So they created an equation to match the energy being emitted at long wavelengths. It's a function of temperature and a function of wavelength. And when you extrapolate that line to short wavelengths, the energy emitted goes to infinity. That's a problem, isn't it? Because no matter what temperature I'm at, I'm emitting an infinite amount of energy at low wavelengths. In fact, in the UV, it always goes to infinity, right? Before you even get to the UV. And so that's what this is called, the UV catastrophe. It's sort of a way to put down their theory. They're like, yeah, their theory was great at long wavelengths, but in the UV, their theory is a catastrophe. And you don't want someone to say that about your theory. And so this was a problem in science for decades. And Planck was chewing on this, and he added in this piece right here, which came from Boltzmann. So this Boltzmann's idea of discrete energy levels is what fixed this. And so when the wavelength gets small, it's up there in the exponent. And so when this wavelength gets small, this piece goes close to 1. And so 1 minus 1 is 0. And so then the denominator, this blows up. And so then the denominator gets huge. And so when you're dividing by something huge, the curve comes back down. And so this Boltzmann distribution allows the curve to turn around and come back to 0, just like experiment shows. And so Planck solved the black body radiation problem, and he'd used Boltzmann's discrete energy levels to do that. And so this black body radiation, some of the observations that we have is that all objects emit light no matter what their temperature. I guess if you could get something down to absolute 0, it would no longer emit light. But every object above absolute 0 is absorbing and emitting light. If you put it in a colder environment, then on average it's going to be emitting more light than its surroundings because it's not at equilibrium yet. And so this is Planck's comment when he received the Nobel Prize. He said, this quantized energy was an act of desperation. Because what are you saying about nature? He's the first one to say nature may be discrete in terms of how much energy it can have, emit or absorb. And that's pretty absurd to say, okay? But it fixed this observational problem. So this was a hint that it might be the reality, right? We have the experimental data and this mathematical model that corresponded to reality, used discrete energy levels. And so are discrete energy levels corresponding to reality? there's a hint here that that may be the case. These discussions were, I mean, boiling in physics. This was one of the most exciting times in science. And this fellow here, Ernst Solvay, was a rich industrialist, and he absolutely loved hearing smart people talk. And this is his estate. He had this huge mansion, and he would invite the brightest physicists of the day to have a conference. These Solvay conferences were amazing. Look at some of the names here. Got Max Planck here, de Broglie here. Let's see, 3 genes for Rayleigh genes theory, and then Ernst Rutherford. He discovered the nucleus. Here's Einstein over here. Here's Marie Curie, Wilhelm Wien, okay, Ernst Solvay, and over here number 6. Who's that? Where's that? Oh, Nernst, the Nernst equation, and there's a bunch of others that are amazing. Okay. Now, another interesting experiment. So black body radiation was the first one. The second one was the photoelectric effect. So here's the data that we see over here on the right. We have the frequency of light hitting a metal surface, and we've pulled a vacuum on that surface, and we put a detector up there above it. And this detector detects electrons. And so we can hit this surface with different frequencies of light and detect electrons that come off. And we can actually measure the kinetic energy of those electrons. It's pretty easy to do that. You have two charged, you can have like a charged hemisphere that's charged positive on the bottom one and negative on the top. And if your metal surface is here, electrons will go between those charged surfaces and hit your detector. And you change the charges on those plates, and you can filter out the different speeds of the electrons. And so you can actually measure the kinetic energy of an electron this way. And so we put that detector up above a surface of metal, we hit it with different frequencies of light, and we see a perfectly linear relationship. So here we have some data for sodium. We have a certain frequency, and the kinetic energy of the electron comes off here. We increase the frequency, and it comes off there. We increase the frequency some more, it has that much kinetic energy. And so what we've essentially proven with frequency and kinetic energy is this linear relationship, and the slope of that frequency to energy conversion is Planck's constant. And so his little elementary quantum of action that he used to solve the blackbody equation shows up here too as the slope of this electron. It's converting frequency of light into kinetic energy of an electron directly. Now there's also down here what we call a work function. Below a certain frequency, we don't get any electrons. And so how might we explain that? We'll look at that in another slide. So we call this the Planck equation, and this is the photoelectric effect. Now think of those words. A lot of these terms that may be new to you, the definition is essentially built into the term. Photoelectric. Photo is light, electric is electrons. So you're hitting the surface with light and electrons are coming off. That's the photoelectric effect. This is a very important effect for this semester's course because we use photoelectron spectroscopy to understand the bonding of electrons in atoms and molecules. So we still use this technique to learn about the bonding. How deep in a molecule are the electrons? Notice this work function, this frequency, that tells us essentially the ionization energy of that atom. And so this is saying that sodium is a little more difficult to ionize than potassium, which is a little more difficult to ionize than rubidium. And y'all memorize those trends in freshman chemistry, right? Well, this is the data for those trends. And so this led, in thinking about this led scientists to think that light must be a particle. So it comes in and hits an electron on the surface, and that electron absorbs all of that energy and comes off with a certain amount of kinetic energy. So that the frequency of a photon is really directly related to its kinetic energy, how much energy that photon has. And the conversion from frequency to energy is Planck's constant. That's delta E up there equals h nu. Okay? And nu is the frequency. Now you can relate that to wavelength by using the speed of light. And the speed of light is defined. It's a constant, a physical constant. It's defined. And this will convert frequency to wavelength. And so whenever you're walking across campus and someone says, hey, what's new? You reply, C over lambda. Okay? And they'll go, oh, you had Dr. Williams. Because that's my joke. So C over lambda. So when someone says what's new, in the graduation picture we yell, what's new? You say C over lambda. My heart gets warm. All right, so they were thinking that this was, particle nature of light. This fit with what Newton said. Newton said light was a particle. Okay? And so everybody in science just knew that light was a particle, and this experiment seemed to confirm that light is a particle, and the name for those particles of light are photons. So it's like Star Trek, a photon torpedo. So you hit it with photons of light. What's interesting too is that the brightness of light, just like if it was more intense, it just gave you more electrons. So it didn't give you faster electrons. So that was an interesting effect out of this experiment as well. Now this is the basis of our detectors. Most of our visible light detectors and our radiation detectors, our scintillation detectors, they have photomultiplier tubes in them. And so we still use this effect in a lot of our visible light detectors, our infrared light detectors, a lot of our X-ray detectors are based on this in some form or fashion, where a photon is converted into an electrical signal. So the light comes in, this metal cathode is negatively charged, and so the electrons really hate to be there. Okay, so that's how you up the sensitivity. You make this more and more negative. And so it's a crowded dance floor of electrons. Okay, and a photon comes in, and those electrons shoot off and hit this plate, and we can detect that electrical signal. We can count individual photons using this. So there are really sensitive techniques. You cool down the photomultiplier tube, you have everything completely dark, and you can do single photon counting experiments.
So you're increasing the charge on the metal?
Yeah, so this is the detector, and so whatever you're doing for an experiment is out here. And then you increase this voltage very carefully so you have a stable signal or no signal. You get right up to where it's about to just go on its own. And so there's really not much holding that electron on that surface, except just the vacuum. And a little photon of light comes on and hits it. And sometimes we'll make a cascade. We'll have a bunch of different charged plates, and this electron hits and knocks 1,000 off, and then that knocks another 1,000 off. So now you have 1,000,000. And then if you hit another 1,000 off you get 1,000,000,000 electrons. And so you have a huge signal. And so it's just one photon can give 1,000,000,000 electron signal. And so that's part of the multiplier part, the photomultiplier tube. And here's a picture of one down here at the bottom. Now let's talk about those energy levels. So if the frequency of light is below that threshold, then we're giving the electron energy, but it's not enough to escape. So light's interacting with the metal surface. Let's say you have an electron down here, and it wants to leave, but it's interacting with light, but it doesn't have enough energy to leave. Okay, and so if light is a higher frequency, then the electron does leave, but it doesn't have this kinetic energy. It only has this kinetic energy. Because this is, they called it the work function, but it's kind of like the ionization energy. right? Because you're stealing an electron and you're leaving behind some charge. Okay. But in a photoelectric effect experiment, it's called the work function. How much work do you have to overcome to get the electrons to come out? Okay. And what's also interesting in the particle view of nature, we can treat that electron like a billiard ball. It's 1/2 mv squared, the classical kinetic energy for a particle that has a mass. So we know the mass of an electron, and we can calculate the velocity that comes out. Or what we actually do is measure the velocity and back into the kinetic energy. And so we use this X-ray photoelectron spectroscopy to learn more about the atoms and the electron orbits in those atoms, but also for molecules. When we get to molecular orbital theory, which you saw in organic chemistry and a little bit in freshman perhaps, you know, you have those different orbital energy levels. How do we know where those are? This is how we know. So we just increase the frequency of light that we're hitting that molecule with, and at certain frequencies, we get electrons out of the pi star orbital. And then we increase it. We need to get it out of the pi bonding orbital. Then we get it out of a sigma bonding orbital. And so we'll see these peaks that correspond to the different bonding orbitals. So this photoelectric effect is a really useful tool. So what about waves? Newton said light was a particle, and I mean, that pretty much settled it. If you went against Newton, you lost. Okay. Thomas Young tried to go against Newton. There was a diffraction experiment. You send light through a slit and you get a diffraction pattern. It's really difficult to describe that using a particle view of light. And so he gave a couple of lectures to the Royal Society, the Baker lectures, and they totally hated it because he used light as a wave to describe the experiment. In fact, they told him in their review of his article that his paper was destitute of every species of merit because he went against Newton. Everybody knows light's a particle. What are you talking about waves? You know, and he was saying that light is also a wave, and this was just totally rejected. And now that, like I said, was 100 years earlier, and so it was time for this wave idea to come back. Particles were successful in describing the photoelectric effect, but we had problems with the electron orbits around the hydrogen atom. And so in some of these later conferences, this is the 5th Solvay conference, we've got some new people on board. Here we have Schrodinger, so Erwin Schrodinger, Wolfgang Pauli, Heisenberg. So these guys are now the fathers of quantum mechanics. And then down here we have Debye, who the dipole moment is, the unit is named in Debye's after Debye. Bragg diffraction. If you've had instrumental analysis, you talk about Bragg diffraction in monochrometers. Let's see. Here's Dirac. Okay, we'll talk about his contribution in a minute. Here's de Broglie again. Born, you've heard of maybe when we get into the Born-Oppenheimer approximation for looking at electron motion versus the nuclear motion. We have Niels Bohr and Max Born. So Niels Bohr came up with this planetary model of the atom that we're about to look at. Okay. And then we have down here Max Planck and Madame Curie and Einstein again, and several other folks that are amazing. So let's talk about the hydrogen atom. You could take hydrogen gas, put it in a glass tube with a couple of electrons and run electricity through it. And it makes kind of like a neon light, okay? Or these fluorescent tube lights that we have in the room. So you run electricity through a gas, you strip some electrons off of the gas atoms, and then when electrons come back onto that atom, they bounce through all the atomic energy levels and give off light as they bounce down. So when you send electricity through a gas, you're learning about the atomic orbitals in that gas because you've taken the electrons off, and when you put electrons back, you get light out. And so this was the first spectrometer, these discharge tubes. And they put hydrogen in that discharge tube, and they got the spectrum of hydrogen. You just run that light through a slit to kind of narrow it down, then you run that light through a dispersing element like a prism, and then you put it on a photographic plate. And you develop that photograph, and you'll see lines on that photograph. And so when we talk about line spectra, that was the name they gave it. If you just have a hot flame there, you get a smear or a continuum. The whole photographic plate gets developed. And you just have light hitting the photographic plate. If you were to look at it visually, you'd see a rainbow, and you'd see all the colors of the rainbow from that visible light. Okay? But if you put just hydrogen gas in there, you get discrete lines on the photographic plate. And so they couldn't explain that. Why, when the electron hops back onto a hydrogen atom, it only emits certain frequencies of light. It doesn't give the full rainbow. It just gives 3 or 4 different colors. Very narrow lines. In fact, it's kind of sad. Bunsen is the one who invented this. Okay? So he invented the spectrometer, but he got the little flame that they used first to use in the spectrometer. The Bunsen burner got named after him. But I'd be ticked. You know, it'd be kind of like you invent the car, but they name the key fob after you. It's like, I invented the whole thing, and you just named the, Bunsen fob. That'd be kind of rotten. But this is kind of what you see on that photographic plate. You see discrete lines that are developed. If you put in a more complex atom, then you get a more complex spectrum. But notice there's still lines. And so this was just a mystery. They could not figure out why we were getting line spectra. So there's this. If you have an electron orbiting the nucleus is positively charged, the electron is negatively charged. If you know something about charged particles changing direction, if you take a charged particle and you change its direction, you're accelerating that charged particle and it emits light. Okay? If you can't emit light without losing energy, and so if the electron is orbiting, it's losing energy and it will spiral into the nucleus. There's no way to prevent that. And so this idea of an electron just orbiting the nucleus, you can think of a tether ball. You ever play tether ball? The ball's stuck to the top of the pole, you swing it around. It doesn't just orbit forever, right? It spirals in and hits the pole. Okay? That's not what we see with atomic spectra. Think of an atomic tether ball. It spins at this orbit, and then you hit it, and it immediately jumps to that orbit. And then it emits a photon of light, a very specific one, and hops down to that orbit. But it never goes down and touches the pole, ever. And so it's just sitting there spinning the whole time. So the old school Bohr atomic orbitals, he said, what if, we don't know why they stay in these orbits, but let's think of it as a planetary model, that the electrons are orbiting the nucleus like a planet. Light comes in, they jump to an outer orbit. When they jump back to an inner orbit, they emit light. And that'll explain the experiment. And it did. It matched the experiment for the hydrogen. And they could actually solve for the radius of these orbits using the charge on the nucleus, the charge on the electron. But they had no reason why the electron would stay in that orbit until de Broglie came along. And this was in his dissertation, so his doctoral thesis. He wrote in his dissertation in 1924 that maybe the electron in this orbit had a standing wave, that it couldn't shrink the orbit because the wave wouldn't match up again. And he was thinking of a violin string and how it has particular nodes and lobes. And so this was that flash of insight, that germ of useful thought. He said, what if the electron around the nucleus is a standing wave? It has a certain wave nature to it. The electron cloud is oscillating all the time. And there's only certain patterns to those waves that you can get. That would give you discrete energy levels. Einstein read his dissertation, which is pretty cool, okay? And he mentioned it to Schrodinger. So Einstein sort of blessed de Broglie's idea, and Schrodinger said, hey, I like that. Let's see if the math works out. And he spent a couple of weeks learning partial differential equations, and he was able to solve the hydrogen atom problem. So just a couple of years later, Schrodinger comes out and solves the the problem of the atomic nucleus using de Broglie's idea of standing waves, which is phenomenal. But it also causes a problem because this treats light as a wave. And that was destitute of every species of merit. Remember? And so we come up with this conflict of light behaving like a particle in a photoelectric effect, or light behaving like a wave in hydrogen spectra, in electron diffraction. Electrons can behave like waves. And so this wave germ, if you want to call it, passed on to Schrodinger, and then here's his solution. So we have the observed and theoretical patterns that we see in the hydrogen atom spectra, and he nailed it. So he didn't just solve for the energies, he solved for the actual intensity patterns. And we're going to learn how to do that in this course. And then Dirac extended this wave mechanics idea, and he went from hydrogen to multi-electron atoms. And that gets complicated. Dirac was probably one of the most amazing mathematicians. And he could see how this wave idea of electrons and nuclei and so on, of atomic scale particles, would really explain all of the quantum effects. In fact, here's his quote. He says, "The underlying physical laws necessary for mathematical theory of a large part of physics and the whole of chemistry are thus completely known." Whoa, that's a quote. This math explains all of chemistry and most of physics. Okay, there's still some questions like gravity and so on in physics that we're chewing on, but all of chemistry is explained by quantum mechanical math. He said, but the problem is the exact applications of these laws leads to equations too complicated to be solved. And so that's the issue. We don't have the computational power. And so later in that introduction, he says it becomes desirable that the approximate practical methods of applying quantum mechanics should be developed so they can explain the main features of these complex atomic systems without too much computation. So Dirac's our guy, right? He's like, we want to have some models that we can work with that don't require too much math. And he's a mathematician talking, but he knows how hard it is to describe every detail. And so he's like, let's back off on some of the details and come up with some approximate methods that can explain the underlying features. And so that's where we are in this course. I'm backing off on some of the mathematical details, like the triple integrals for the hydrogen atom, and I'm going back to one dimension, which is an approximation. But I can, with that one-dimensional math, describe the main features of the atomic world. And I want you to come with me. We're going to learn that deeply. We're going to learn a lot. Next week, we're starting lab with the calculus of one-dimensional quantum mechanics. Okay, so if you're Monday, Tuesday, or Wednesday lab, show up your lab time. It's going to be in 101 with the TA, and we're basically starting with a couple of. It's a dry lab. It's just math of this, and you'll have a lot of time with your TA and with your peers to work through the problems. So it's going to be a good session where you review some of your calculus, but you'll apply it to the quantum world. And then we'll get into the applications and the various spectroscopic methods throughout the semester. So hopefully this gives you an idea where we came from. Math was found to be useful by Descartes. We have Cartesian geometry. Newton explained everything but the atomic world. And as light interacting with matter gave us insight into the atomic world, we had to come up with an expanded theory that took into account discrete actions of nature. And so that's where we are in quantum mechanics, is trying to understand how light interacts with matter and how that tells us about the tiniest particles in our universe. So hopefully you enjoyed that, and we'll see you next time on Monday.